But, I don't know.
I'll never get this right.
Which one?
It's like this changes every time I try to do it. There we go. Let me take a picture of that. Okay. Sorry to be late today. Almost everybody has an approved project now. So well done getting to that point. If you don't have a point assigned to the proposal project, then it hasn't officially been approved. So take a look, make sure that you've got that. If you don't already have a point, then there are comments I've made within Canvas on the assignment about some aspect of it. So you need to respond to those, and then I'll just let you know. Once we get to a point where it can be approved, I'll say it. You get the point, and then your project can go along. So make sure that you've gotten that far. Like I said, I think there's only like 2 projects that are in that are not yet approved. So good job getting to this point. The projects are pretty exciting. I'm looking forward to seeing how those turn out. Okay, we're getting to the end here, aren't we? I'm at the end of the lectures. we're getting to the end. So we've done a lot of different things. We mostly focused in while learning, deep learning, on supervised learning. We've done a couple weeks now on supervised learning, and we're now going to move into reinforcement learning. So yet another learning paradigm. Sorry, I guess I just failed to generally ask. Any questions before we get started? There might be. Yeah.
I've been seeing some stuff about like bootstrapping labeled data sets when you don't have any like rule-based systems. I've never seen that kind of stuff before, and I'm wondering if you have any comment on it.
Yeah, I mean, there's all kinds of systems that could be considered under that name. Where I thought you were going when you said bootstrapping and labeling was this idea of pseudo-labeling, where people do this kind of thing where you have some labels that some labels only, or some labels that you're confident in, and then you train your model on those. Then you make predictions on the rest of the unlabeled data, and for those that you have like high confidence in, you then add those to the training set and you kind of iterate until you get to a point where you can't add any more confident labels. In general, that seems to work well. I don't know all the use cases, but this is like a pretty common technique in like places like Kaggle for like winning Kaggle competitions, like trying to label the test sets and things like that. Yeah, I mean, it seems to work really well. If you have any more specific kind of question on that, maybe just come after class and ask me. But yeah, there's a lot of ways of trying to add labeled data where there doesn't seem to be any, without going through the costly part of actually having like a human annotator. All right, good question. Any other ones? All right, reinforcement learning. So like I said, we've been doing supervised learning. We've just been through some ways of doing unsupervised learning with neural networks. And now we're going to talk about reinforcement learning. Okay? So, reinforcement learning is a different paradigm. You are going to see lots of things that you recognize. We're going to be setting up loss functions. We're going to be training models with these kinds of loss functions. But in general, the setup here is a bit different, where we are going to have some concept of an agent, or even multiple agents. They exist in an environment of some kind. some sort of world, and they interact with that environment. And as they interact with the environment, they get rewards for that. And this is the idea of reinforcement learning. It kind of, goes back to like, the ideas of like positive or negative reinforcement. You make a decision, you get some feedback on that, whether positive or negative. That you use that feedback to adjust how you would do, what you would do in that situation the next time, so that you can like maximize that reward or reinforcement. So in general, the way this works is, we're going to need to specify our environment and how agents interact in that environment, basically what actions they can take given the state of the environment, and then how it updates the state of the environment and how that provides a reward to the agent. And then the whole goal here of learning, the task here, is to like learn to take actions given the state of the environment so that we're maximizing our reward. So of the other, of all the learning we've done, this should look a lot more like, I don't know, how you typically think of learning, right? Like this is like, think of this agent as you, and think of the environment as your world, and think of like rewards as like, everything from like the grades you get, assignments to just like, like the positive or negative, kinds of feedback you might get from like social interactions, whether that would be on social media or just like in the good old days, just being with a person in, like in person, things like that. So, but in general, because we're doing this, with machines, we're going to be looking. These environments are going to be very, very like closed in the sense like it's going to be very well defined what the environment is, what actions you can take, how that turns into rewards. In fact, we're going to be mostly motivating this with like games. Games are, already are set up with well-defined environments, well-defined actions you can take, and usually well-defined rewards. But we'll see lots of different examples. Okay, so we'll do, we'll talk a little bit more about what reinforcement learning exactly is. We're gonna pose some like theoretical underpinnings. We're gonna look at what's called a Markov decision process. We're gonna think about the act of like the agent making a decision. We'll formulate it as a Markov decision process. You may or may not have seen this before. And then we're going to get into one of the ways of doing reinforcement learning, in particular deep reinforcement learning, with the idea of Q learning or deep Q learning when we use networks to do the learning of what's called a Q function, or Q value function. Anybody already like seen any of this stuff before?
Yeah, this is in 4300 and 6300.
6300. Okay. So if you're taking 6300, you might like already know everything here. If you haven't, good for you. This is your first time. Never forget the first time being introduced to reinforcement. Okay. So agent environment. Like the basic kind of setup here is that the environment provides a kind of state. So we will think of things temporally here in the sense of, the environment will be in a certain state. We'll make this a little bit less abstract here in a second as we look at examples, but it'll be in a certain state at some time. The agent then, is going to at that time make some sort of decision depending on that state. So the agent needs to be able to look at the state, needs to be able to observe the state, and then act on it. And that action is going to possibly update that environment to a new state. And when we get to that new, before we get there, taking that action as as we're now updating the state, that's also going to produce some kind of reward at that same time. And that's fed back to the agent. This is in the simplest case where like maybe every single action actually provides some kind of reward. Often when playing a game, there isn't, for example, when playing a game, you can think of this like many games, there's not a reward for many of the actions that you take during that game, like the reward save comes at the end of the game, whether you won or lost. There might be like intermediate actions along the way. Maybe like a different example to think about here is self-driving cars, right? So the environment is like the state of the roads that you're on, and you might actually be rewarded at every step where you take an action if you are like you haven't wrecked the car, or you're not driving too close to somebody else, or you're not making like an unsafe turn or something like this. There might be you can think about there being like intermediate reward, but like the ultimate reward being that you got yourself to the final destination safely, right? So you can have all kinds of ways of structuring rewards to be able to reinforce good actions taken and like deter bad actions taken. Right. So once that loop's gone through, your environment now is in like a new state. Think about like if you're playing a game, maybe you're playing chess, you move to peace. The state of the board's changed. That piece has moved. Or you're driving and you stay in your lane, like you don't make any change. The environment's changed because you've now moved forward on that road. Maybe also different cars around you might have started to change lanes or slowed down or sped up or something like that. So all of this is part of that environment. And then we just kind of like stay in that loop. For historical purposes, this carpool problem is like one of the classic examples of like doing reinforcement learning. So, have you ever seen the carpool problem before?
Isn't this just balancing an inverted pendulum?
Yeah, it's just balancing an inverted pendulum, right? So, an inverted pendulum, if everything's like, all the forces are equalized, and that pendulum is standing straight up, this is like an unstable equilibrium for this system. And any sort of perturbation from that will cause that pendulum to fall to the left or to the right. Now, the whole thing about putting this pendulum on a cart is that the agent has the ability to now start to move this cart around, to the right or to the left, in the simplest example of just having this kind of 1D environment to work on. And the idea is, given the state of things, right, like where the pendulum is now, like in this case, in this frame of reference compared to pointing straight up, what forces we're currently applying to the cart, moving it to the right or to the left or something like that. We want to be able to take an action at that point, change the forces on the cart, so that pendulum doesn't fall down but like stays up. Okay, so this is like a very like classic kind of control problem, dynamic kind of control theory, and the reward is you're rewarded if that thing hasn't fallen down at every time step, right? So this thing is like, if you're making decisions so that it's keeping that up, then you're winning. This is like a really classical way of doing things, but this is not the way that we evaluate good reinforcement learning agents. There are far more interesting, useful kinds of things that people will evaluate their algorithms on. One that you see quite a bit. You see these kind of fun videos of either humanoid or arachnoid or whatever simple kinds of objects that can move, that have arms or legs or some way of moving the object, and often these things are subject to just like basic laws of nature, right? So there might be these are obviously simulations, but like some like gravity, having gravity as a force on whatever the object is. But the idea here is that you typically want to like get get the thing to learn to move itself to some other place in the environment, like in this crazy chessboard world. And at first it doesn't know how to do this. Like it just, it just knows that it can like, whatever like the body type of where the joints are, like there's ability to apply some force, like a torque, to change the angular, or change the angle between two connecting pieces in the joint. And, subject to whatever sort of physical laws, this thing now has to learn how to, apply those torques, basically like, move the joints so that it learns to get itself to another, to some other location. And basically in the process, like especially for this kind of humanoid objects here, like learn how to walk, like learn how to, keep itself upright and walk. And did we watch any of these at the beginning of the semester? These are really fun to watch. Do I have this linked? Hold on 1 second. Maybe we'll play after ad. Great. This lecture brought to you by Nationwide. Okay, here we go.
Should you like put a regularization to penalize like unnecessary movement?
You could, but that's giving it information that this thing doesn't need to, or like, it's building a prior into it, right? This is like learning completely fresh.
Squid Game?
You just love the music. It's like you're watching. Yeah, but see, it's staying upright.
So this is a player against environment, but not players against other players.
Yeah, this is not necessarily a game, right? Like the reward specifies how, what actions you take. So this is a stay upright, get to a certain part of the. I love that one. It's fascinating, right? Like we all kind of take walking for granted, but there's really a lot of ways you could walk and stay upright. Especially if you were just a torso.
Is the floor moving?
Oops, bye-bye. But the point is that like it's, every time it fails, it gets a negative reward or doesn't get a positive reward. And it's able to use that information to then adjust itself. However the learning happens. In our case, neural networks that'll map the state to the action. And you get all kinds of wild behavior. I mean, if you saw somebody walking like that, you'd think something's wrong. However, it's not wrong. It's a perfectly plausible way to walk. Cool. So again, that is just, that's kind of older work now for DeepMind. Simply reinforcement learning, simple state space, all the positions of the joints, and like where it is in the system. You saw far more complex environments with gaps they had to jump over, with walls they had to kind of go around, like hurdles to get over, things like that. But in general, like the kind of learning that we're doing here, just as long as you can specify the state well enough and specify how to map states to actions, you can learn to do all kinds of things. Just, if you have the reward right. In this case, this is quite easy to think about how to do the reward, right? You want to stand upright, you want to keep moving in the right direction. You've probably seen a lot of this before, but like, DeepMind started doing a lot of work just trying to play like very simple kinds of games. Basically like all the Atari games that were ever made. What's nice about this is that people a long time ago built emulators for this, and so like the environment exists, like all the rules, like how to take actions, all this like already exists. You simply have an agent in there that takes the state and turns that into an action, and literally that the action is like, think about like, I don't know, I'm way older than all of you, but like I can totally remember playing Atari with like the old joysticks and paddles, and you're literally the action is, what do you do with that joystick? It used to be paddle, you turn like this, like you turn to the right, turn to the left, or you move the joystick to the left or right, up, down. Sometimes there's a button, you press the button. Like that's it, right? And what you're trying to do in these things often is just like, usually it's like give the maximum score, right? So like you can give an intermediate reward of if you increase the score, or like if there's a way to determine if you like won the game, like got to the end of a board, or got the high, got to a certain score, say in like Pong or whatever, then there's this like ultimate reward of, hey, I actually like won the game. And so this is like a pretty awesome playground. In fact, there's something that OpenAI put out called Gym that basically allows you to like easily work with all of these kinds of games. But a great place for reinforcement learning, but basically like completely solved at this point. Like completely solved. Like you can have agents that know nothing about the the rules of all of these games, and like learn the rules and then learn to play according to those rules, like at the ultimate expert level, master level. So pretty cool. This was followed up, with far more complex games, chess and others, but then of course Go in 2016 is like totally amazing ability to play and beat grandmasters in Go. I mean, it's quite an amazing story, quite a feat of engineering as well, how that was done. This makes it sound way too simple. It is way more complicated than this. Like what they had to do. But again, pretty much solved in the sense of there are systems now that can play at the grandmaster level that never play another human. They play itself and really learn the rules of the game and then learn to play at the master level. So basically completely solved, all with very sophisticated reinforcement learning. There's even more wild things let's see, do I have this link as well? This is really also pretty fun. Also brought to you by Dick's Sporting Goods. So everything up to this point has basically been like a single agent. Like you're playing it, you're playing a single agent. I mean, you might be playing against somebody, but that's part of the environment. But you can have multiple agents working towards common goals, where they all get rewarded as a group. And this is a really cool, a little bit older now, demo, playing hide and seek together as teams. And so here we go.
Incomparably simple rules and multi-agent competition can also lead to intelligent behavior in a new.
It also it doesn't hurt if you work for a company with massive budgets where you can put together these amazing demos. Because certainly this is not what they were watching. They were playing the game. This is something you created after the fact. But anyways,
virtual world.
Deep body.
Agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and blocking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at disposal.
Did you hear that? How many games do they have to play to figure that out?
Millions.
How many games would you have to figure out? How many games would you have to play to figure that out?
Well,
Yeah, 1, 2, or something like that,
we
right?
have a huge prior.
What's that?
We have a lot of priors to help us figure this out.
Yeah, exactly. So this is one of the massive, kind of word's not complaint, but one of the big problems with the way reinforcement learning currently works, and that is, it takes a million plays to figure out that, like, hey, they're jumping over with this thing, and I can go get it and move it. Where like for a human it takes one or two. So like it's massively inefficient in terms of learning. Like this is the most inefficient way of learning anything. Reinforcement learning is in general. Supervised learning in general is like the most efficient way. It's unsupervised maybe lies somewhere in between. But it shouldn't take a million games to learn that you can just move that ramp in, right? And so a lot of research goes into, maybe it's about priors, about like understanding a little bit more about the world, but like how in general can you get these things to learn more like a human, where they can take, some kind of common learned understanding, like what for us might be like already in our genetics, right? Like we're already kind of wired to understand things like basic physics and and those kinds of things. And be like how can these things, how can these agents kind of come to that and be able to be thrown into many different kinds of environments and then very quickly adapt to those. So just so you know, that's out there.
Note that we do not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt.
You see how there's like this adversarial aspect of this? There's multiple agents and they're both learning at the same time. So there's this adversarial thing where it's like, like the generator and the discriminator, right? Generator gets really good, and the discriminator, gets really good, and the generator gets really good. Sort of the same thing here, but they're just like, two sets. In this case, two sets of multiple agents that are being rewarded, separately, and kind of basically like an inverse to each other. Like, if blue team's doing well, it means the red team's doing bad, and vice versa. So, things that we've already learned about, like adversarial learning, that happens here as well.
It's into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learned. However, we found that after more training, the seekers discovered that they can jump on top of boxes and serve them to the hiders' shelter.
Isn't that cool? Like, this was not an expected behavior, but it's allowed in the environment.
The hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing.
So why don't we just lock the
two agents
seekers?
acquire these skills. They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents played thousands of rounds of hide-and-seek in parallel for many days. They trained against each other, as well as past versions of themselves, using an algorithm called self-play. Co-evolution and competition on Earth led to the only genetically intelligent species known today, humans. While this world is far less complex than Earth, we have found evidence that simple rules can lead to increasingly intelligent behavior from multi-agent interaction.
I mean, this is like the most subliminal kind of messaging ever, right? It's like,
Diverse environment.
we are such a wonderful company.
Agents.
We produce
One day, emerge.
green worlds. Open AI. Alright,
Look at this. 94% of people.
thank you. Alright, so you get some flavor of like the kinds of things that we're trying to do here, okay? I think reinforcement learning is super fun for this reason. Like lots of possibilities for emerging kinds of behaviors. Unfortunately, this comes at the cost of like a lot of training. A lot of training. So you need to be somebody like an OpenAI that has access to, basically unlimited Azure resources at Microsoft after Microsoft agreed to basically invest $1 billion, worth of value into OpenAI. Right? So in general, like many of these things will be beyond, just because of the computation required, will certainly be beyond like your collaboratory resources. You're going to have a lot more resources to get these things to the kinds of, be able to do these things from scratch, like play Go at grandmaster levels, or have teams of hide and seekers, play at these like ultra expert levels. But below, underneath it all, there's just this kind of common setup of there being a state, actions you can take in that state, rewards that you would receive for that action, and then the updating of the state. So actually this fits really well into a well-studied kind of structure known as a Markov decision process. So I think we've probably mentioned the name Markov a couple of times. When you see it in computer science and math and statistics, you might know what you should be thinking when you hear that word Markov. When someone's described as being Markovian or having like the Markov property, I guess it's written up there. But have you seen this before? Yeah.
Yeah, for like language models, it's usually like a first order Markov model is when the current state only depends, well, the next state probably only depends.
Yeah. There's a real kind of simplification made here, which is you only need to know the current state to make like an optimal decision. You don't need to know like the past history of what the states that you've been in. You only need to know like the state of how things are now. Yeah, those ways set up here characterizes the full state of the world. So these are not, so Markov decision processes are ways of making decisions when the current state is is all you need to make an optimal decision. And mathematically this looks like this tuple here. You have sets of possible states, sets of possible actions, your reward distribution. So we're going to use the word distribution here because we're often going to have rewards made like, we're going to allow for the possibility of those rewards to be given like randomly in the sense of being drawn from a distribution. So with some expected reward, but allow there to be some variance in how that's done. Transition probability. This is also characteristic of Markov process. Is that you have a probability of transitioning from one state to another given the action that you take. So again, we're going to allow that to be. Usually, you think of this as being deterministic. Most, like a lot of games, like that's the case. But say like if you need to roll a die, that determines the action, right? There's going to be a 1 in 6 chance of getting one of the numbers, and that that adds some kind of randomness. That's why there's a probability in terms of how you transition or how you transition the actions that you might take. And then there's this thing about a discount factor that we're going to get into. But this discount factor is a really important part of reinforcement learning, how we specify the rewards. And there's this idea of we're going to look out into the future and think about how does the decision we make right now, not only just what reward does it give us now, but what rewards could it give us in the future. We're going to basically average over all possible trajectories. We're going to attempt to do that. That's theoretically how we're going to do this. But the further out a future decision is from us, the less we're going to weight that in terms of how we make a decision now, right? So this discount factor allows us to kind of reduce future rewards according to how far in the future that decision will be, right? So it'll allow us to feed back that kind of information. You'll see kind of as we go through here how that works, but it's going to allow us to feed back that information, but allow us to discount the fact that it's way off in the future, and if it's really far off in the future, it probably shouldn't have any kind of bearing on what we do now, unless it's a really large reward, which allows it to overcome discounting. So, anyways, this is a part of So if you have this set of 5 things, you've got what's known as a Markov decision process. Okay. So how does this work? So you start at the beginning, time step 0, and you have some way of starting from initial state. You might sample that randomly from some distribution of your state space. That could just be deterministic, in a game the board always starts in a certain way. There are, you think of chess as being that way, but there are lots of different versions of chess. One bizarre version of chess is having randomly starting, initial positions for the pieces. Then for time, time 0 is like this iterative thing. You're just going to do exactly what we saw those little state diagrams for. Our agent's going to look at that state and is going to select an action. that action is going to be rewarded depending on the current state and the action. We're going to then sample the next state. That could be deterministic. Like there's only one state we could go to, or there could be maybe a distribution over the state space that we could go to next. And then the agent receives that reward, and now we're in this new state. We're just going to keep doing that over and over. That's the basic kind of iterative process here for the Markov decision process. And then we're going to have, very key to this whole thing is the notion of a policy. So a policy, well, you're going to see pi here, this Greek pi as a variable used to indicate a policy. This is a function from the state space, right? S is the space of possible states, to A, the set of possible actions, that specifies what action to take whenever we're in that state. So it's a function from states to actions. And really, what we're trying to do in a Markov decision process, like a common objective here, is to find or learn a policy that we have here as pi star that maximizes this what we call the cumulative discounted reward. So this is the rewards. Like you can think of this process right here as generating a trajectory of rewards. Right? Every time we take a new action, we get another reward. This process will generate a sequence of rewards, a trajectory of rewards, and the cumulative discounted reward is to sum all those up, but to discount them by how many steps in the future, exponentially discounted by this discount factor, according to how many steps in the future they are. Right. So you have this. So gamma. I guess I didn't have that on the slide. Gamma is between 0 and 1. So this, the idea of it being a discount factor is that it's going to be discounting or reducing these rewards, and so this infinite series here is the cumulative discounted reward. Notice that this is assuming this is the discounted reward for one trajectory. What we're really interested in is because there's stochastic processes in here, is the expected version of that. So really, we're trying to maximize the expected cumulative discounted reward, given the stochastic nature of the rewards that are given, how we update the state space and things like that. So these are all just kind of set up to just think about all the things that are important when doing the Markov decision processes that we'll use to help us analyze what we're doing in reinforcement learning. Questions up to this point? We did on time. All right. So let's look at this really simple setup for a Markov decision process. So what we want to do. So here's our state space. We can be in any one of these grid points here. Okay. So those are states. Our objective is to reach one of the terminal states, so that's the one that has the stars in it, that's grayed out, in the least number of actions. We can take these 4 actions right here. We can move right, left, up, or down, and we're trying to, wherever we start from, we're trying to get to one of those starred, grayed out grid spaces. So, this is a Markov decision process because you can the action that you take there depends only on where you are right now, not the trajectory you've taken in the past. And if we think of this in a reinforcement learning way, we're going to want to do provide rewards. In this case, because we're trying to do this in the least number of actions, we want to penalize this thing for taking any action at all, right? Because every time you take an action, you're less likely to be to have taken the least number of actions to get there. So the way that this reward system will work to obtain this objective is to provide a negative reward every time we take a step. Then we want to maximize that, right? So maximizing that means take the least number of steps, take the least number of actions. Okay, so this is pretty simple. Like, how should this work, right? If I'm right here, what decision do I make? Do I go left? Do I go right? Or do I go up?
It doesn't matter.
Yep. In this case, it doesn't matter. Let's say the reason for that is because it's going to take 1, 2, 3 steps from here to get to there, and 1, 2, 3 steps to get to there. If I'm right here, left, right, or up. What should I do? I can't go down, but walk up, and the environment prevents me from doing that.
Up or right.
Yeah, like don't go left, right? Up or right. Will put me on a trajectory to have the least number of steps to get to one of the grayed out spaces. If I'm on the grayed out space, I'm already there. That's pretty easy. So what we were starting to work out there is what an optimal policy would be like, right? So given the state that I'm in, what action should I take? Well, when we were here, it didn't matter if we went left, right, or left, up, or right. So there's a distribution here that's uniformly distributed over those actions from this state space. I can choose any of those with like the same probability, and those would all be optimal in the sense that I can still have the least reward no matter which direction I move. But if I come over here, that's different. If I move left, that would not be optimal. It would take too many steps than the least path from here. So I can go up or right. So the policy from this state space would assign a probability of like 1/2 of going right or up. If I'm in any one of these steps, there's one decision I should make. If I'm below, go up. If I'm to the left, go right, and so forth. So it's pretty easy in this really simple example to figure out what is our optimal policy, what is our pi star here. This is quite different from say like some random policy that just assigns equal probability to all the actions we can take in each state. We are not likely to traverse the least number of steps to get to one of those end states in that way. This looks like a random walk. In general, that represents not making optimal decisions. Okay, super simple. So in general, this is what we're trying to do. We're trying to find the optimal policy. Markov decision process. We're trying. This is like what the theory is all built up for. We're trying to figure out how to identify this and an optimal policy given the Markov decision process. Again, this maximizes the sum of our rewards. We could have done rewards for this simple thing in a different way, and we get a different optimal policy, right? Like if we wanted to be the longest path possible, well, that would be ill-defined. We could make this infinite for some of the starting points, or I guess for all the starting points, you can make this infinite. But I don't know. You could come up with all kinds of ways, and that would change all kinds of ways of stating the objective, and that would change the optimal policy. So given the objective, we want to be able to maximize the sum of our rewards, the expected cumulative discounted reward. So how do we handle randomness? Well, this is like I've already started saying this. Like we actually want to maximize the expected sum of these rewards, the cumulative discounted rewards. So basically what we're trying to do. Given the stochastic nature, the possible stochastic nature of our Markov decision process, what we're trying to do is maximize the expected cumulative discounted reward over our space of possible policies, where the initial state is drawn from this distribution, where actions are drawn from our policies, and where the state space is updated according to our state in action. So it's kind of ugly. There's a lot of terms to pay attention to, but like this is like the theoretical thing that we're trying to do. Maximize this expectation with respect to policy, with respect to the decisions that we make, given the state of the environment. Does that make sense? And we've chosen this to be the thing that we're maximizing. We could have chosen something else. Any idea why we choose this? Like, what's another option that we could have done?
We could have minimized loss, and you can define loss as negative reward.
Okay, that would be basically the same. But yeah, I mean, you're thinking, that's good. Any idea why that? They're all mathematical, basically. One is, if I have, just for the mathematicians in the room, like, if this is like pretty well behaved, like if this gives us finite, like bounded finite reward. So like, if our rewards can never be larger than, some finite reward. And then I have this gamma right here, which is something between 0 and 1. And I'm looking at this infinite series, and I'm summing with respect to the exponential, or so like the powers of this discount factor.
So you want it to be
What? Yes, I heard it from the mathematicians in the room, at least one of them. This series converges to a finite number. Okay, it's really easy to show. Just take absolute values. This thing is bounded. This thing, will converge to some finite number. Easy to show. So first of all, like as long as your rewards are well behaved, this thing converges. Like this is an actual number given all kinds of policies. So that's one of the reasons why it's like this, mathematical convenience. Why else? Why like this form right here? We could have done other things with the discount factor.
Yeah, can you just do 1 minus c raised to the t instead, or c is the interest rate instead of the discount factor?
Sorry, say it again.
Instead of doing gamma, you could do 1 minus c, or c is the interest rate.
Oh, okay, yeah, sure. I mean, it's equivalent, right? Like conceptually, it's equivalent. Like mathematically, it's equivalent. You were saying something, Kristen?
Maybe it's no different than saying it converges, but we know what that converges to since it's geometric.
Mm-hmm.
Yeah.
But
Yeah. Like we can actually compute what it converges to. At least like the bound on it, we can compute. These things might be kind of wild, so it might be hard to actually do. But at least it does converge to some fixed number. Well, one of the things is when you have things of this form, and you have sums, like you can do things like multiply by the whole thing by a gamma, and change the sign here really simply. You can factor it out and change the sign. I meant the exponent here. You can do all kinds of things that, like simple arithmetic operations in this geometric series, that like are really convenient for things like recursive formulas and things like that. And it turns out that this is going to be the key to like learning these things is that we're gonna see here in a second. We're gonna put together like a recursive formula that's going to allow us to guarantee convergence of a thing called a Q function, and ultimately it's going to come down to the fact that like the form of this thing here. So like a lot of this has to do with mathematical like convenience, as with most like mathematical theories.
So why do we need it to converge? Like, can't we just let the reward diverge to infinity, and then just compare like how quickly it diverges? So we just pick the one that diverges the fastest.
Yeah, that you could do something like that. But basically, what you would be doing in that case is changing this so that your reward is no longer the reward, but like the derivative of the reward or something like that. In which case, you'd be right back into the same situation. So yeah, you can play all kinds of games, but in the end, like really this, like that particular example reduces to this again.
Well, in that case, if they're all diverging, but you see like some reward path that converges, then that's the bad one.
Yeah, you know what? If you want to make that your life's work, go for it. It'll be fun to see what happens there. But yeah, like in general, while you could do all these other things, this is like oh, we forgot one thing actually. This sort of makes sense. right? Like this sort of makes sense. Like it like fits our intuition. Rewards in the future should matter, but they should matter less than like immediate rewards now. Like in general. Of course, you can come up with exceptions, and you know, you can play Socrates and whatever here, but you know, like in general, that makes sense. It kind of fits like a notion of how we think about decision making, which is, you know, think about the future, but you know, like those rewards, because they're so far out, sort of have less of an impact than like, you know, like what's happening now. Those are assumptions that we're making here. You could change the assumptions, you'd get a different theory. Just saying it out loud, so that's clear. Okay, so what? It's all just, you know, pushing symbols around. All right, well, we need to be able to do something, you know, useful here. And so what happens is, again, it shouldn't be obvious why you would do this. You know, right away, this is like worked out over however many years of people thinking about these things. And of course, a lot of this thinking happened decades and decades ago. It's only like the using deep learning to learn like these kind of functions that we're going to describe next, where like you get the innovations that allow you to do things like win and go. So if we have a policy, we're producing a trajectory of states, of actions, of rewards, and you know, keep going, right? Like there's this, you know, there's this kind of trajectory, and it's probably stochastic, right? Like if we started from the same state, we might take a different action, we might get a different reward, but in general, you know, like we're these agents generate, you know, these trajectories of state action reward triplets. So, you know, a question we might ask ourselves within this theory is, how good is a state? Well, what would that mean? So we have a notion of what's called a value function, pretty generic term here. For a state, the value function defined on our state space looks like this. So again, so this is, you know, given a policy, that's what you see over here. Given a policy and an initial state. So notice that this is like a function on the states in our state space. So if we start in that space initially, what is our expected cumulative discounted reward? All right. So the value function says for a given policy, it assigns a value to that state, which is the expected cumulative discounted reward if we follow that policy, having started from that state. Right? So in that trajectory, like we're specifying the very first state and allowing the agent to go from there. And the behaviors of the agent are described by the policy. Okay? Again, pretty theoretical. Like at this point, you should be wondering, like, could we even ever like compute these things? Like if the reward's kind of wild, like even if it's well behaved in the sense like that thing converges, like so what? Could we ever even get a hold of these things? But you know, conceptually, this kind of makes sense, right? We can assign a value to this, like some real number to this, and this makes sense. It's consistent with all the other things that we've been talking about. Like it's consistent with our objective. Okay. Another thing you might ask is, how good is a particular state and action pair? Right? These are the things that matter. We're in a certain state and we take a certain action. Like how good is that? Well, it's very similar. So what we have now is a Q-value function. So it's like the value function, but instead of it depending on the policy and the state, it now also depends on an initial action that you would take. Okay? So again, it's the expected cumulative discounted reward given, an agent, a policy, and a fixed initial state and a fixed initial action. So again, like in this trajectory up here, we're now fixing both the initial state and the initial action, and then asking what's the cumulative reward. So again, very related to the objective of maximizing that whole thing, but it's just saying, okay, like if we have a particular policy, a particular state, a particular action, how good is that? Again, no easier to compute this than this, or I don't know, maybe you fix one more thing, so maybe it's easier, I don't know. But like, they're both pretty abstract concepts at the moment. If you knew these functions, you could do a lot with them. Like these could be used to find optimal policies, it turns out. And how's that done? Well, that's where we're gonna go next. So, this is really important to the theory of like Markov decision processes and reinforcement learning. This is known as the Bellman equation. What we're going to come up to next. This is not the Bellman equation. We're going to get to it. So, the optimal Q value function is the one associated with the policy that maximizes this function, maximizes the Q value functions for a given state in action. Okay, so whenever you're seeing star here, this is something about being optimal. So for a given state in action, the optimal Q value function Q star is just the maximum expected cumulative reward achievable from a given state per action. Okay, so you're maximizing this thing with respect to the policy, given a state in action. So that probably related to something good here, like the objective is to maximize this over a full trajectory, not just given us an initial state in action. But what does this allow us to do? Well, interestingly, this optimal Q value function satisfies what's known as the Bellman equation. And the Bellman equation looks like this. This actually is a recursive formula. And what this is, so here's Q star, this is recursive, because here's Q star again. And what this is now is saying that we can compute this by computing an expectation over the possible state spaces I could take next, given our initial state and an action, where we are, the expectation now is over this value, the reward given the state in action, and then a maximization of the same thing again over the possible actions I could take with this discount factor out the front. And I try to set things up, as I was talking earlier, getting you ready to think about the fact that there's going to be a recursive formula coming up, and the pieces are all here for you, right? Like you can think of this as something like taking this sum right here, taking the first entry in this series at t equals 0, gamma to the 0 would be 1, and reward at time 0 is r naught. We sort of drop, just for ease of notation, we drop the zeros, but initial state, initial action, initial reward. So that's like dropping that, and that would leave now the series starting at t equals 1, which would be gamma r1 plus gamma r2, or gamma squared r2 plus gamma cubed r3 and so forth. You'd have that, and if you can just picture it, if you just from that series starting at t equals 1, if you factor out that gamma, you now have something that looked like that expected that expected cumulative, or just the expected cumulative discounted reward, but starting at reward 1 rather than at reward 0. So that's like the recursive part here. What it's saying here is, like, the intuition for this is, if the optimal state and action values for the next time step are known, then the optimal strategy is to take the action that maximizes this expected value of this formulation of the expected cumulative, or sorry, just of the cumulative discounted reward, having already taken one step. So you maximize this by maximizing all the other steps you take after having or maximize the Q value, over all the other actions after you've taken that first step. So it's just recursive. Like, I get the maximum value if I start from an initial state and then I maximize everything else beyond that. Questions? Is there any kernel of like believable thing here? Or is it just kind of like too opaque and just kind of believe like, yeah, math happened, that makes sense?
Would you mind going through the equation one more time, please?
Sure.
Just the,
sure, no problem.
the part after gamma.
Yeah. So I think the most important part of building up the intuition is to think about why this term is here, right? Is right here. Okay. So remember, for a Q value function, you're assigning a value to an initial state in action. Okay? That's what S and A are. You're assigning. Now, once you have a state in action, you're going to have a reward. Okay? Now, if you look at this thing right here, do we even have a working pen? We usually do. If you look at this thing right here, oh good. I apologize to people who are not here. You can't see that. But, this is our cumulative discounted expected reward, right? Now, this is equal to the first term, t equals 0. Gamma to the 0 is a 1. We just left with an r0. And then this looks like this. T greater than or equal to 1, gamma to the t RT, right? And this is just simple math. And then what I can do here is I can factor out a gamma, right? This all converges nicely, so I'm able to do this kind of factoring out over an infinite series. Mathematicians nod their head, thank you. Okay, it looks like that. And basically, this term right here looks like this term right here, just that like we're starting not at time 0 but time 1. Right? Like what I can do is I can rewrite this one more time. I have a gamma here, and I can write this, t greater than equal to 0. This would be a gamma of t, and this right here would be RT plus 1. Right? So this term right here, again, like you kind of have too many lines here, but this term right here looks like this term right here. It's just that we're starting like one step ahead. Right? So that is essentially what is here, where we've now replaced, we replaced this sum with like the Q value, the optimal Q value version of it. And what we're saying is we get an optimal Q value for an initial state in action if we now go like, we take, we accept the fact that we have the state in action and we get this reward for it. If we now look at all the other actions we can take, and we maximize that with respect to the action for the next state, right? So this is an expectation over possible states that would occur, given the action we just took, and then we're maximizing with respect to the action we take from that state. So that's basically like replacing this term right here with its optimal Q value, where the state is coming from, being drawn from the possible next states, and the action is just that's what we're maximizing for. So if we take, like, in this expectation, given one of these states, if we take the optimal, or we take the action that maximizes our optimal Q value function, then we'll have actually maximized the whole Q value function. Does that seem believable? I mean, this is not exactly a proof, but this is also not that kind of class, I guess. So hopefully get some sort of intuition from that. Why a recursive function? Why is that a good idea? Like, who cares? So what? Again, I'm going to sort of rely on the mathematicians out there. Applied mathematicians. Anybody? What's good about a recursive formula?
We can select one sample at a time and update the Q function.
Or if you find like the base case, you can kind of grow it out.
Yeah, it suggests an iterative way of solving the equation. So, oh, sorry, I have one more thing here. Yeah. Oh, yeah, this is important. Sorry. So what if we could do this? Well, the optimal policy. So if we know the Q star value, like the optimal Q value function, then we actually also know the optimal policy. Because what it does is it corresponds to taking the best action in any state as specified by the optimal Q value function, right? So, if I'm in a particular state, I can just I can look at this thing. I can compute all the across all the actions. I can compute these values, and the one that I take is the one with the highest value. But the action that I take, and if I do that, I have an optimal policy. That's another proof that we have. Sorry, that's probably me again. You need to just waking you up. Okay, so if we can, if we can solve this thing somehow, we're in good shape. Now, if we have a recursive function, then there is and like this function is it has some mathematical properties, like basically that it's contractive mathematically, but whatever. Just believe that it is. There's an iterative way of solving this. And it's the following: that we compute. Like what we're going to do is we're going to compute a series or a sequence of Q value functions that, in the limit, is going to converge to Q star. Basically, this is going to give us a sequence, and the thing that this is going to, as I goes to infinity, is something that actually satisfies the equation on both sides. Like the Q star would go in here and here. So if you have these nice like contracting functionals, then this happens. But just believe that this algorithm in general will work. So this is cool. So like this is like, there was all this abstractness. We didn't prove it, but we suggested that you could prove that there's this recursive function or recursive equation known as the Bellman equation, which is awesome because now we have this algorithm for solving this. So, like, we're done, right? Like, this is it. Now we just iterate this thing and all's good. Unfortunately, there is a problem here. What's the problem? Thoughts?
Maybe we have a large state space, so
Yeah.
getting enough samples to calculate the optimal Q is feasible.
Yep, that's you're right along. It's the right idea. In general, solving this iterative equation is not scalable. It is scalable, like you could do this by hand for like the simple grid world that we looked at, right? No problem. But in general, if this is a very complex, if it is a very complex state space, if you have a lot of complex actions, like computing this is actually just completely, intractable. For instance, if your game state is described by like all the pixels in your Atari game, like the arrangement of all those pixels, like there's going to be a lot of states, and being able to compute this for all the actions for all the states, this becomes like a combinatorially large problem. You can't do it. Okay, so has anybody been missing deep learning for the whole lecture? I certainly have. There hasn't been any deep learning at all in here. What are we going to do? That's right, you knew it was coming. We are now, what we're going to do is we're going to approximate our Q function here. We're going to estimate it with a neural network. Whenever things get too complex, whenever we talk about pixel state spaces, you should just know that the solution now is a neural network of some kind. Okay? And how does this work? Well, this is what's known as Q learning, or when the Q is a neural network, a deep Q learning. We're going to use a function to approximate this Q value, okay? So like, basically what we're going to say is, there is, this is a parameterized function. There's a set of parameters that would allow us to either be the optimal Q value function or approximate it pretty closely. And neural networks are awesome that way. They're often really great approximators. So again, like if your parameterized function Q theta is a neural network, you're doing deep Q learning. And how does this work? We need a loss function. Anybody missing loss functions? I certainly was. So I would not be earning my keep around here if we didn't have a neural network or a loss function somewhere. So what are we going to do here? What we're going to do is we're going to basically we have some parameterization of our optimal Q function. We want the left side to be equal to the right side. So we're literally going to subtract the two, square it, and have that be our loss, so that we do gradient descent, so that the left-hand side and the right-hand side are like coming closer and closer together. Meaning like they're going to zero, and if they're exactly zero, then we have this equation, and if this equation holds, and if they're really close, then it's approximate. But like probably good enough, right? So awesome. Well done, deep learning. Way to get it. And of course, people had tried to do this already for other kinds of parameterized functions. Think about all the earlier ML things you might have learned, like SVMs and things like that. But of course, could not learn the complexity of these kinds of relationships. But deep learning allowed us to do that. And there you go. Once you have your loss function, you just compute gradients, and you take gradient. This is stochastic gradient descent, exactly the same ways that we've already studied, and voila, you're doing. You're learning this. You're learning this loss. You're minimizing this loss function. You're learning this Q. Once you have this Q, or something very close to the optimal Q value function, you now have an optimal policy. All right, I think we've run out of time. Let me just see here. Yeah, but what we'll do is next time we'll start with just these examples. Okay? I don't want to start now because